and I want to do a little bit of AP Physics stuff. Okay, so we'll look at some momentum stuff here and there and get some ideas of what's going on. Okay, to start, what we've already done in momentum is we have looked at this equation that Ft, a force across a time, equals m Vf minus Vi, because m times F is a momentum. We know P equals mv. And we know force times a time is an impulse, J. That equals a force multiplied by a time, which is equal to a change in momentum. So normally this Ft equals m Vf minus Vi. It's not that bad to do, but this V, or this F here, is technically an average force, or it's a constant force. What we can do to kind of mix up the problem, and we did a few of these in class, is if we have some sort of function here, or some sort of curve, then we run into a bit of an issue, because this F times t, this impulse, this really represents some sort of area. We're looking for an area here. And that is the area of a force time graph. Now, if I have a weird shape like this, a weird curve, the quickest and simplest way to do it, if you're familiar with it, is calculus. You integrate that function through your bounds. Unfortunately, we don't know calculus yet. So how can we get the area underneath this curve here? That's the bit of the issue we've got. So we have a way to do this. If we follow these 3 steps here, we'll be pretty fine. Our first thing to do is to figure out how much impulse, how much area does each block represent here. So if I color in this one block here, and things got weird on me, that was strange. If I color in one block, what's its area? Okay, well, zooming into this, I see this goes up 1, 2, 3, 4, 5 hundreds there, so that means this piece right here is at 100. And if this is 1, 2, 3, 4, 5 to 0.005, that means this is 0.001. And if I do 100 times 0.001, well, there's 1, 2, 3, 1, 2, 3. Each of these blocks, 100 times 0.001, each of these blocks is going to be equal to 1 Newton seconds of impulse. Okay, so I know that 0.1 Newton seconds equals the impulse of one block. Now for part B, we need to estimate the total impulse applied to the bullet. So what is the impulse applied to the bullet? Well, I know one block is 0.1 Newton seconds. It's just a matter of counting the blocks, finding that total area. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, about 15, 16. That's a pretty good block. Maybe this one and that one is 17 and a little bit. Maybe 17 and a little bit, 17 and a half. Maybe I've got 17.5 blocks. And since each block is worth 0.1 Newton seconds per block, from what we have up here, then I can say that, hey, I've got about 1.75 Newton seconds of total impulse. That's the total area underneath this curve here. Okay? If I want to find what the mass of the bullet is, I know whenever the bullet leaves the barrel, it leaves with a speed of 680 meters per second. This value here is the impulse. It is J. J represents Ft. So it is this whole thing here. So what I can actually write for part C is 1.75 Newton seconds equals the mass of the bullet, which I have no idea what it is, we're looking for it, times, well, the final velocity. We know it leaves the barrel with 680 meters per second worth of velocity or speed, and its initial was 0 because it was just sitting there in the gun. So since that's subtracting minus 0, we actually don't even have to put that. It doesn't do anything. And to find the mass of the bullet, we just have to say that m is equal to 1.75 Newton seconds divided by 680 meters per second. I get something along the lines of a mass of 0.00257, round that how you will, kilograms. Okay? We know we're looking for an impulse. That's one block here, just like we saw. We can count the number of blocks for a total area, get a total impulse, and throw that in our momentum impulse equation, the same one we've been using for everything. So with that, that's a simple little impulse momentum for a strange function, something that's not a constant, to do. If we had a nicer graph and it was just like a triangle or a square, just find the area of a triangle or of a square. 1/2 base times height for a triangle. For a square, just length times width. Add up all your shapes and that will give you the total area, which is the total impulse of this system. Okay? So with that, we're done with this. That's Finn. Okay. Let's see, rocket.